So that is how you design Turing machines to do computations. And as you see, it's not very trivial, even with relatively simple tasks. A Turing machine for multiplying two non-negative integers has 31 five tuples and 11 states. So it's quite a complex system, even for such a simple task. And even more complex tasks, you will have much more complex systems. On the other hand, if you define a multi-tape Turing machines, the design can be simplified. I'm not going to show examples to this, but you can look it up. And essentially, it can be shown that for any multi-tape Turing machine, there is a one-tape Turing machine that can do the exact same thing. So it's again not a new type of Turing machine, but it's an alternative representation of the original Turing machine, but it reduces the complexity of the design, so you can use it instead of an original Turing machine. Also, if you recall the non-deterministic finite automaton, in the similar way, we can define non-deterministic Turing machines. In this case, the transition function, recall that it's already a partial function, which means there are some input configurations where the next transition is not defined. But if you relax that, you have to have a unique transition for each configuration, you end up with a non-deterministic Turing machine. And again, in most cases, designing non-deterministic Turing machines could be easier than designing a deterministic Turing machine. Now, Turing machines are the most essential units of computation. And a Turing machine is capable of doing any task a digital computer can. This is not an exaggeration, and it's not an approximation. So it's the perfect mathematical model for computation. And that is the elementary unit researchers in theory of computation use to model digital computer systems. Of course, in theory, we disregard the practical time and space limitations of actual computers when we model them as Turing machines, because in principle, a Turing machine has infinite memory because the tape is infinite in both directions. But of course, real computers have finite memory, but usually our models disregard this shortcoming. Now, how do we use Turing machines in modeling computation? First of all, a programming language is called Turing complete if it can be used to simulate any Turing machine. This means a programming language is Turing complete if it can do any task that a digital computer can do. Obviously, you would like this property in a programming language, and naturally, virtually all have this property, and some of them theoretically do not, but when you relax the memory limitation, when you ignore the memory fails, some of them also become Turing complete. And we have the concept of decidability and computability. If you remember our discussion when we talked about proofs, we have seen that mathematics is not a really complete system in the sense that we cannot really prove everything in a consistent system. And here we are going to see that we cannot really compute everything. A decision problem asks whether statements from a particular class of statements are true or not. So this is a problem where you need to decide a yes answer or a no answer. And if there is an effective algorithm that decides whether instances of a decision problem are true, we say that this problem is solvable or decidable. For instance, given a positive integer, is this number a prime number? This is an example of a decidable problem because you can always decide whether that number is a prime number or not, even if by dividing it by each possible positive integer smaller than this number. Obviously, that may not be a practical approach or an efficient approach, but that is not the issue here. The issue is it possible to solve it or not? So that problem is a decidable problem. But for instance, the halting problem, this is a very famous problem, again laid out by Turing, is the decision problem that asks whether a given Turing machine eventually halts when given an input string X. So consider you have a specific Turing machine and consider you have a specific input string X. The question is, if I provide this string X to the specific given Turing machine, is it going to halt? So this is the general setting of the halting problem, but Turing showed that the halting problem is undecidable. So we cannot really solve this problem for every possible Turing machine and every possible input string. So this is an example to undecidable problems. Another concept is computability. A function that can be computed by a Turing machine is called computable. And of course, a function that cannot is called uncomputable. Again, we have computable and uncomputable functions. And in fact, there are infinitely many uncomputable functions. It's not that difficult to prove this. In fact, there is an exercise in Rosen's book. If you are interested, you can have a look at that. But the concept here is the essential tool or the essential machinery to represent in a mathematical way a computer is a Turing machine. And based on this mathematical model, we can actually classify problems as decidable or undecidable, or problems or functions as computable and uncomputable.